Magnetic force. Now, a lot of this lecture is going to be very reminiscent of what you learned in Physics 2. This lecture is going to serve mostly as a review of that material, plus formalizing of some of the stuff. So the basic formula for the magnetic force is F is equal to Q times V cross B. This is the cross product. I know that both of you are either in now or have been in statics, so you know what a cross product is and how to use it. As a brief reminder, if you have two vectors, in this picture, vector A and vector B, vector A will have I, J, and K components, vector B will have I, J, and K components. Put them in a matrix like this, with the I hat, J hat, and K hat forming the top row, and the determinant of that matrix is the cross product, or written out more expansively, the J component of A times the K component of B minus the K component of A times the J component of B is the I hat component of the result, etc. We also will, a lot of times, use the fact that a cross product, the magnitude of a cross product, is equal to the product of the two magnitudes times the sine of the angle between them, and then use the right-hand rule to determine direction. We will be doing that less in this class than you did in Physics 2 because we are trying to be more formal, but that is still often an option. As a reminder for the right-hand rule, you take your right hand, take your thumb points in the direction of velocity. The mnemonic I like to use is when you're hitchhiking, your thumb goes out, that's the direction you want to go. Thumb is the direction of velocity. Your fingers form the magnetic field. So think of them as the magnetic field lines, bunch of field lines, bunch of fingers, that's that. And your palm, you push with your palm, so the force is in the direction of the palm. Now also keep in mind, in this equation there is Q times V cross B. So V cross B will always have a direction given by the right-hand rule. But if we are dealing with a negatively charged particle, such as an electron, Q is negative, which means the direction goes in the opposite direction. You can either use the right-hand rule to find the direction of force and then invert it, it goes the other way, or you can say electrons are left-handed and then use the left-hand rule, where you use the thumb and fingers same directions as before. When a magnetic field acts on a charged particle, if that charged particle is not moving or is moving parallel to the magnetic field does nothing. However, if the charged particle is moving perpendicular to the magnetic field, what happens is the magnetic force is always perpendicular to the motion or to the velocity of that charged particle. Because one result of a cross product is that the resultant vector, C, is perpendicular to the two inputted vectors. So C is always perpendicular to both A and B. So if you're moving in a magnetic field perpendicular to that magnetic field, the direction of force is perpendicular both to your velocity and the velocity of the and the direction of the magnetic field. So since the force is always perpendicular to velocity, that means that absent any other forces, a charged particle in a magnetic field will move in a circle, with the magnetic force providing the force required for the centripetal acceleration of a circle. Now we can get more complicated. The particle might have a component of velocity parallel to the magnetic field and other components of velocity perpendicular to the magnetic field. In that case, the perpendicular components will cause the particle to move in a circle, but the parallel component will remain unaffected. The net result is the particle will move in a helix. Magnetic force can also apply to current. Now this is another one you learned in Physics 2, dF is equal to I dl cross B. What this is saying is that for a small piece of the wire, it creates a small amount of force. And if you want to find the total amount of force on the wire, you would need to integrate both sides. Now there is a little bit of a convention screwiness going on. Most textbooks will insist that this is the proper way to write it. That the current is not a vector, that it's the vector of the wire itself. So you have to write it like this. Our textbook says that it's actually like this, and just by convention, because current is constant in a wire, make it a constant value, push the vector to L, claiming that it's just a way to do the math. See equations 5.15 through 5.17. The reality is neither of these are actually good ways of doing this. They're not perfect. They're usable. In order to be entirely consistent, we actually need to skip to this last one, where the small differential force depends on this quantity right here, which is called the current density. And you can say that the current is equal to the current density integrated over the entire cross-section. That works fine. You could also say current is current density of a delta function. That is also fine. And quite frankly, any of these ways you use, you will still get a usable answer. So yes, to explain some of these symbols, I is the current. That's, like you learned in physics 2. K represents surface current density. So see equation 5.22. That is if instead of a single line wire, like you would use in this formula, you have a flat sheet that carries current, in that the current density per unit width is K. And then finally, real wires are, in fact, three-dimensional structures. Current does flow through them. And so J is the area current density. You can think of it, if for a constant current density, it's the total amount of current divided by the cross-sectional area. But J can vary with position, so it is an area density.